And good morning, everybody. So we have made it to our final lab Friday. So I also expected, I've heard a lot of rumors of a really big circuits assignment that was coming up this week. So I expected a low turnout today. But what I would like to do is I would like to go over a couple of things. I want to hit on the Towers of Hanoi problem and describe how it is that you can use stacks to be able to perform tasks, particularly with recursion. So that problem is a really good way of combining a lot of different concepts that we've gone over during the course of the semester. And then the second thing I want to briefly touch on, it'll take just a few minutes, is this idea of namespaces and why it's, if you've looked online at code in C++, you'll often see something called using namespace STD. And you probably noticed that in my code, I almost never use it. In industry, it's considered bad practice, and I'm going to show you an example as to why and ways that you can kind of get around how they're not using namespace STD can make your code tedious at times. All right, so the Towers of Hanoi problem. So how many of you are familiar with the Towers of Hanoi problem? All right, so most of you. So most of you are familiar with this animation that I'm about to do. You have 3 different poles, and the whole idea is that you want to move all of the plates from one pole to another pole, and we have a few restrictions. You cannot put a plate that is bigger on top of a plate that is smaller, and they have to end up in the same order. So whenever we move from one to another, it has to be in that specific way. So the solution, the most efficient solution will be we move blue over to pole 2, then we move this one to pole 3. Now we are in a scenario where we can only move elements to a smaller one on top of a larger one. So we would move this over here. Now we can move the red one there. And then our only thing that we can do is move blue over to pole 1. But now we've set up where we can finish our solution. We can move the yellow to pole 2, and then we can move blue over to pole 2. So the challenge of the Towers of Hanoi problem is I should be able to do this and figure out a solution for any given number of plates. So the question is, how can we do that? So first I would like to show you how I've coded up a solution here. Should actually open the code. Let me actually open Hanoi too. So I first created a tower class. And I call the tower class, I have a private member, tower num. And the only reason I have that is because I want to be able to print out to the user at the end the entire trace of which poles we need to move to. So given a certain number of plates, I should be able to see every single element. So we would be able to print out the size, and we would be able to print out the specific pole that we're at. For simplicity, I made stack a public member. So that way I can just access the stack's members. So I just have an actual stack inside, and then I have my constructor. Here I call it an overloaded constructor. In this case, I don't have a default constructor because every single time I would want to create a pole, I want to have a number that defines that specific pole. So I only have the overloaded constructor here. And then the only other method I have is I want to be able to return tower num. So I call this method here. So that's how I can encapsulate all of them. So in order to solve this problem, I need 3 of those. So that's one of the first things that I do in Hanoi.cpp. Let me scroll past the other functions here. I just want to go to main where I start. So I start out and I'm going to read in from the command line the number of plates. So I have my int argc and here start argb. I do my test where I say if argc is not equal to 2, we have the incorrect number of inputs, and I probably we just have exit -1 there too. Make sure I have C standard lib here. right, so I'm going to go back down to main to just show you how I started out. So I have the total number of plates, and we wrote a big function earlier this semester about how to read in elements and read through the characters and be able to build. There's a simple function that does most of the work for you. It's not foolproof, unfortunately, but I just want to, in this case, I'm going to put in correct arguments. This ATOI stands for ASCII to integer, and it reads in a character array and outputs a valid integer. So I showed you some examples of that. If you try putting in, if you put in 10.1, it will lop off 0.1, or if you put in other values, it's not perfect. But for our cases today, since we're just trying to present a simpler solution, this is sufficient. So I call it int stack size. So that's the total number of plates. And I also initialize an integer to keep track of the number of moves. The next thing I do is I create 3 stacks for the 3 rods. So I have create tower, tower 1, tower 2, and tower 3, and that creates 3 stack numbers, and it also has an integer indicating what the tower number should be. We see that I have 1, 2, and 3. And so no matter how many plates I have, that we should be able to come up with a solution that can do this for 3 poles. Now here, what I want to do is I want to show you a for loop, and I have an animation that describes what this code does. But basically what it is I'm starting at stack size. So if I say stack size is 3, it'll be 3, it'll push onto the first pole, it'll push 2 onto that first pole stack, and then it'll push 1 onto that first pole stack. And then I'm going to run the Hanoi algorithm, which I'll describe in a little more detail. Come on, there you go. I went, well, that goes way too far. There we are. Okay, so what I just described for you, if we have Hanoi at 3, it's going to say arg c is not equal to 2. Now stack size is going to be equal to 3. Num moves is equal to 0. Then I create 3 towers. Then I say stack size is 3, and then I'm going to push an integer on there to represent 3, 2, and then 1. Now we're at 0, and now it's going to go into the Hanoi algorithm. So what I'm going to show you here is an example of a code that does a movement. So what we're going to have is we have 3 poles, and the way we can describe a movement is we have a source, a destination, and then we have an auxiliary pole, which we're not doing anything to. And so in this move function, I'm going to show you up close, and then I'll show you the animation. So that's the one that's here at the beginning. I call a tower by reference. I call 3 towers by reference: tower source, tower destination, and int moves. So then I say, I increment the number of moves, and I say I move that move. So it'd be move 3, for example. Weight is going to be source, the stack dot top. In fact, I'll zoom out a little bit so it's clearer. The source dot stack dot top is the integer at the top. And then it's going to say from tower get num, destination tower get num. So it's going to tell me where I'm going to move to. And then I get the element at the top of the stack and I push it onto the destination. And then I pop it off of the source stack. So it's going to look like this. I increment the number of moves. And then here's the store stack. So initially it's going to be 1. It'll move it to the destination. So at this point, I have a duplicate. And I account for that by doing pop at the end. So this particular portion of the code here, and let me go down to the function Hanoi, which is here. This is a recursive call. And this is all the code that's required to actually run the algorithm itself. I have an int n, tower, source, destination, and auxiliary. I've called all by reference, and num moves. And what's going to happen is I'm going to start with a certain size, certain height. And that's going to be the current height of the tower. And while it's greater than 0, I'll say n minus 1, and then I say source, auxiliary, destination. So what happened is in the function call, I have source, destination, and auxiliary. So on the left, I flip auxiliary and destination. And on the right recursive call, I flip auxiliary and source. And so we just keep going all the way through there. And in between, when we have the middle, we would call the move function where I would move one plate to the other. So what I want to do is I want to show you the animation that goes through this. Okay, so let me click through all that. So here, I'm going to show you the actual thing. So we start out at n is equal to 3. That's the number of elements in the stack. So then I would say, all right, well, I do n minus 2, and then I flip the source and destination. So if you look at the arrows, you'll see that I move down, and it was initially, I'll show you, let me point this out just so I'm clear. It's initially source, destination, and auxiliary. And then when I make that left call, it flips the auxiliary and destination. And then it just keeps going until we hit 0. We hit 0, it's going to just say, I'm going to go back up. So now we go back up one level to H1. And now we call move. So we have source and destination. So that's why 1 is going to go here initially. Like so. And then if we go right, we're going to flip source and auxiliary. So we see we go to 0. And then we go up here, and now we have our source and destination with 2. We see that 2 is going to move to this plate. And then we go to 1, and now we're going to do the whole thing again. And now we get to this right location. We go to 0, we move back up, and now we're here. We have our source and destination. And as we've hoped, the blue plate is going to move on top of 2, like so. And then we go here, now we're up to 3 again. Now we're going to do all the right calls. So now we're going to flip source and auxiliary. Oh, I'm sorry, we have a middle move first. We have to move 3 over. And then we do 2. We get to here, now we move it over. We go to 0, we don't do anything. Now we're going to move up to 2. We hit our middle movement. So now we have source and destination. We see that 2, the second plate, is going to move on top of plate 3. Then we make a right call. And now we've solved the problem. And now it just makes all our recursive calls and removes everything off of the instruction stack. So what I'd like to show you next is I'm actually going to compile and run it. Right? And then if I do Hanoi 3, it shows me all 7 moves. Now, since I don't want to take up too much of your time, so you can focus on the lab, the way it's going to work is the number of moves will be 2 to the n minus 1. So in the case of 3 plates, it'll be 2 to the 3, which is going to be 7. Now, if I do 4, it'll be 15. So let's see what happens here. Hanoi 4. And we see that it takes 15 moves to be able to solve the problem. If I did 5, it's going to be 32 minus 1, so it'll be 31. This will be 63, 127. Now I'm doing 10. Now I'm doing 15. And the reason why it was initially called the Towers of Hanoi is a rumor that, well, it means a urban legend that there were monks in Tibet who were moving plates, and what they've actually successfully moved all the plates in the correct order, then that would be when the world would end. So we solved the problem for them so we can make the world end sooner. But we see here that even at 15, it's going to take a long time. That's going to be 2 to the 15 minus 1. So the question is, how robust is our machine? We understand that with our machine, that we have a certain amount of limited space in the instruction stack. And if you were to go on further, if you were to take a logic design course or a computer architecture course, you would learn that we have all this cache memory. I kind of briefly showed you that, where I showed level one instruction, level one, we get level 2 and level 3, and then we get into main memory. So here I just have a significant amount of time that it's taking, and it's actually taking a lot longer because I'm printing out every result. This probably would have been solved by now, but it's using recursion in a way, and I'm going to stop it, Control C, and run make clean here. All right, so did that make sense to everybody? That's kind of just a good way of saying, like, okay, there's the call by reference. I don't have to do all this dereferencing every single time. We've learned about recursion. We can see how recursion can actually simulate what's going on in the real world. We saw an object-oriented approach to it. So we were actually representing plates. We were representing towers. And we saw how using the C++ standard template library was able to simplify our particular problem. So we use that standard stack in order to solve it. Okay, so the second thing I want to talk to you about is this using namespace std. So in C++, what they do is they have all of the functions in the standard template library in what is known as a namespace. And the whole idea is that if you call the namespace, then you don't have to do things like standard : because it will just find all of the methods in there or functions, for example, cout, and say, well, I was using namespace std, then I can just write the function there. So it's there initially, it's usually introduced at introductory courses to simplify the programming. However, the bigger issue is that it's generally considered bad practice in industry. So you get out into industry and you'll see really quickly that they'll want you to kick this habit. So I want to take you really briefly and show you why this is. The reason why is because of something called namespace pollution. So often you get to your, if you're running in C++, the companies want to build their own namespaces. They want to make things proprietary. They want to make things simpler. And the issue is that while they're doing that, the C++ standard library is still evolving. So what ends up happening is that you might have a namespace that you've defined unintentionally. It'll work for like standard C++ 2011. So what you have in your makefile. But then let's say they add several new functions to the 2020 standard that was going to be rolled out, but unfortunately was delayed by the pandemic. They might put more functions in there, and if you have two namespaces overlapping, what will end up happening is that it won't recognize which one to use. And so let me show you an example of namespace pollution. So in this particular code namespace.cpp, I have a namespace here, and I call it namespace foo, and I have a function called cout. And I'll just say return 10. And then in order to get it to recognize, I use using namespace std and using namespace foo. And then I call cout, and then cout with a function call. Just like when we were dealing with overloaded functions and had to differentiate that we couldn't use const or non-const, so the same variable because it's ambiguous to the compiler. And this is going to give us a compiler error saying that it's ambiguous because it's not going to be able to figure out which cout to use. So let me make namespace. And we see that it in fact gives us compiler errors. Reference to cout is ambiguous. And so it's trying to figure out all the different ones. So extern ostream cout is what's going on in the C++ standard template library. And I've been defining in a lecture with standard : : You've been doing the same thing in your classes when you split it up into .cpp files. Like for example, you were doing bin node : : So that's kind of, you're doing the same thing that's being done in the C++ standard template library. So one way to solve this would be to say, all right, I'm going to take out the using namespaces, and I'm going to use standard : here. So I use standard cout, and then foo cout, like so. And so what's going to happen is when I compile make name good, we're going to see it's going to compile and it's just going to print out 10. So it's now able to differentiate between them. So there's two common follow-up questions. And the first question is, I think I'm disciplined enough to not use cout and endl in a function name. Why is it still bad practice? So like, why can't I just put in using namespace STD? I think I have the discipline. It's not because of you. It's because of C++. C++ is constantly evolving, and there might be a function that you write in a namespace that was okay for a certain standard, but is no longer okay for a future standard. And one big thing in industry with code is something called a code's life cycle. How long will the code be viable for us to use? And using namespace STD puts your code at risk. Right? So that's why it's not something that's about you, it's something about the standard in C++. So the second one is, okay, well, that's all well and good, I understand that. But putting standard : cout before everything is pretty tedious. Is there any way that I can come up with a way to do this without having to do that over and over again? And sometimes when I'm really tired, I've had an electronics exam, and I got to write your project, and I got to do all these other classes. Sometimes I'm fighting through it, and it's just tough. Is there any way that I can simplify this process? And there is. And it's going back to our to what we've done earlier in the semester with this _define. It's a compiler directive. What we can do is we can say _define variable meaning and variable name and then the meaning. And we can use this to simplify the program. So here I have an example of _define cout standard cout. And in the code, in namegood2, I do the same thing. Note how I have 3 compiler directives here. This means that anywhere you see cout, the compiler will replace it for you with standard cout. So you can actually just say uppercase cout, or you can say uppercase endl, and then allow the C++ compiler to do that rest of that work for you. So you can maintain, you can contribute to code that is that doesn't contribute to namespace pollution. So the code that you have is better structured, is considered good practice in industry, but you can reduce the complexity by using these _define directives. So going all the way back to what we were learning in C. So what I want to do now is I want to show you how it works in main in order to provide clarity. So anytime we see cout, it's going to replace it with cout, and anytime we're going to have endl, it'll replace it with endl. So down here we see, and the other directive, excuse me, foo_cout is going to be foo cout here. So when I go down here, we see that I say cout, foo cout, and endl. So if I was writing a big program, I could just type cout in uppercase and not have to worry about keeping track of that standard : because the compiler will do the work for us. So when I run make namegood2, that will also compile and run 10. Right, does anybody have any questions about that? All right, so the last thing I'd like to do is I would like to work with, kind of walk through lab 12 and what it is that I'm expecting and give you some examples that you can go back and look on here. So this is going to be, I've alluded to this idea of dynamic programming that's built upon previous, it's a solution that's built upon previous solutions. And so first of all, I have all the directions here for lab 12 and where to get all of the code using wget. And you've used dynamic programming twice already. You use dynamic programming to solve the Fibonacci sequence in order to get the fifth element. In the Fibonacci sequence, we need the third and the fourth. We just add those and get them. And also that using the process of push and pop to be able to determine if you had valid brackets in your code. Because once you removed it from the end, then you had a sub-solution that you're still working on. And all you had to do is make sure it was empty by the end. So if we had a solution to a certain point, we didn't have to keep track of anything else. We just said, oh, it's so far, it's so good, it's so far, it's good. Either we figured out it was not good or we kept going. So that's the general idea behind dynamic programming. So that's what I described here. So now what I want to do is on our last lab, and I provided you a lot of the code to set it up. Basically, you just need to implement the actual algorithm, is a problem known as the longest increasing subsequence problem. And the way the problem is stated is given an unsorted array of values, find the length, and I have it highlighted here because that's going to be important, of the longest increasing subsequence. So for example, I have 10, 9, 2, 5, 3, 7, 101, and 18. And what you're going to try to figure out is 2, 3, 7, and 18. That's the longest increasing subsequence, and they don't have to be together. So the unsigned integers here, I have another one, and the output is going to be 4. And the reason we'll know it's 4 is because I have 5, 8, 9, and 11. And I have an explanation here. I say, well, why is it not 5, 8, 9, and 12? But the reason why is if I put 12 here, it wouldn't catch it. So what I'd want to do is I'd want to say, well, now I want to do 11 and 12. So now that my output will be 5. And that's what I kind of described here. And then I have another example here with ASCII characters. In this case, A, B, C, D, and E is the longest increasing subsequence. So what I want to do is I want to walk you through how to apply this. So this would be a problem, and if I were giving it my data structures course, that they would need to actually figure it out or not. What I'm going to do is I'm going to walk you through it to kind of help you, so to strengthen your computational thinking here at the end of the course. So let's see how we would do this. So in the brute force approach, I'm going to bring up, and I want to copy and paste here. So if we were saying, all right, what's our worst case approach? Well, what I would do is I would start at 10, and I would say, well, 10 has 11 and 12, right? So the longest increasing subsequence here would be 3. We see that I'd have to iterate through all of them, then I have to move to the next one and iterate through all of them. So to do this at 5, I would say, well, 5, 8, 9, 11, and 12. So that's 5. And then 8, there we go. 8, I say, well, that's 9, 11, and 12, that's going to be 4. 3, that would be 3, 4, 11, and 12, that's 4. 9, I would say 9, 11, and 12, so that's 3. 4, I'd say 4 and 11 and 12, so that's going to be 3. 12, you say that's 1. We'd say this is 2 because it's going to be 11 and 12, and 1 is going to be 1 itself. So what's going on here is we see that there's a potential pattern, right? And that potential pattern means that there are solutions that are building up here until we find our biggest possible solution. Does everybody see that? So we have a potential for trying to figure out how to make this work. And that's kind of what I describe in detail here. I actually go through the entire process where at 10, we would add 12. So let me show you what I'm doing here. I'll just go through the first one. So if I'm trying to come up with a solution here, I'd say we start at 10. And we're trying to figure out the longest increasing subsequence that has 10 in it. I say, I go find the next one, and I say, well, here's 12, so that's the next bigger one. And then I find 11, that one's smaller than 12, right? So I'd say, all right, well, I'll replace that one. And then I'd find 12 here and put that there. So that's what I'm saying here with add 12, remove 12 and add 11, add 12. And what I've done in the highlighting is I pointed out, if you're writing these things up and trying to solve these problems for those of you who come to me and ask about job interviews, it's okay to say, all right, I'm going through a brute force approach, and you start writing an inefficient solution, but you start seeing patterns. If you start seeing the patterns, that's where you can apply some computational thinking towards more advanced solutions. And so where I have the green and yellow are actually the same task over and over again. Add 12, remove 12 and add 11, add 12. You see that over and over again. So here, and this is what I just drew out for you, the comparison of the longest increasing subsequences. And then I actually did the same thing for the other examples where that would be the longest increasing subsequence starting from there. So what we're going to do is we're going to focus on keeping track of an ordering, and all we need to do is keep track of the length. So if we're keeping track of the length, this makes the problem significantly simpler because all we have to do is figure out a number of the length. We do not have to return the actual elements. Does that make sense? So here's what we're going to do. And I'm going to walk you through my steps here because I want this to be clear. What's going on is we are going to, if the number is smaller than the largest element, we're going to just overwrite one and have a sorted order at the end. And if it's bigger, we're going to put it onto the back of a vector. So here's what I mean. We start at 10 and nothing's in there, so we put in 10. So 5 is now smaller than 10, so we're going to overwrite it. Did we see that? So 8 is now going to be bigger than 5, so we just put 8 at the end of this vector. So 3 is smaller than 8, and we keep going, and now 3 is also smaller than 5, so we go until the point where it's no longer smaller, and we overwrite that one. You see that? What do we think is going to happen with 9 now? Someone tell me what they think is going to happen with 9. Yes. Very good. That's what's going to happen. We're going to put 9 here. And so now what's going to happen with 4? And again, let me press escape so that way those of you in the chat, you can, oh, I completely missed a, what about 5? And Peter, can we come back to your, okay, never mind. Yes. Okay, cool. So here I had 3, 5. That should be 9. Okay. So here we have 9. And now what's going to happen with 4? What do we think is going to happen with 4? I'll call somebody else besides Henry. Who else wants to guess? What do we think is going to happen at 4? Yes. Very good. That's exactly what's going to happen. We would say, well, it's smaller than 9. It's smaller than 8. It's not smaller than 3. So we replace 4. All right. So now, since you had your hand up, what are we going to do with 12? Very good. So now we put 12 on the back here. And so now what are we going to do with 11? Yes. All right, so I want to correct one quick thing. You are right that there is 9 and 12 between is a crucial aspect of it, but we want to overwrite 12 in this case, since 11's smaller than 12. And now we have 12 at the end, so what are we going to do here? Yes, push it on the back. So this is sufficient to solve the problem. So that's how we can say that we know that the length is going to be 5. So in order to actually break it down, we have to do more complex stacks and pointers and put them into piles and be able to have the pointers point to the specific ones. So we're not going to deal with that. That's a bigger data structure. But as long as we can come up with a, I'm sorry, I just saw the chat come up here. Why is 8 going to be in there if it is before 3? So let's walk through it again. So we have 10, then we overwrite with 5, right? Then we go to 8. 8 is going to be bigger than 5, so we put it there. Then we have 3, so then 3 is going to overwrite 8. We have overwrite 5. Then we have 9, so now 9 is going to be here. So now we have 4, so 4 is going to be overwriting 8. Then we have 12. Then 11 is going to overwrite 12. And then we put 12 onto the back. Right, Peter, did that address your question? Okay. And so what I've done in the description, and so that's my description of how the algorithm will work. So the question becomes, well, what happens when you have a really large array? So we need to figure out where the smallest one is. And we've done this earlier this semester. We went over this sort search, right? And sort search, excuse me, in sort search, what we did is we had this function find element. This is where I refer you to in the description, where what you're doing is you are doing low, high, and middle, and you're trying to find the element. You find middle is equal to high plus low divided by 2. And here I'm printed out so you can see in lecture, you can see the whole thing. But here what you're doing is you're finding the search val. We print out that we found it. And then we want to return these values at the end, right? So what you're going to do is you're going to make a modification. First of all, so we're going to bring it back up here. Here we go. So what you're going to do in the steps to completing the lab, you're going to write 2 methods, and the method call is already provided for you. So you're going to pass the vector. You say get longest increasing subsequence. It's returning a long unsigned int. And what you're going to do is you're going to iterate through the vector. You should create a vector to store those LIS elements, just like I've shown you. And then if ILS is empty or the current element is greater than the last element, then you push it onto the back. Otherwise, you're going to call this find and update element that I've passed to you, where the element should be updated and then you return the size of the vector. The second one, find and update element, I have a search val, and that's what we're going to be passing. That's the one that we now know is going to be smaller than the last element. So then we're going to do this divide and conquer approach to find it. And then I say, review lecture 17, slides 22 and 31 go into a lot of detail. And then sort search find element function. Note that the size is the size of the vector. So in that find element, we had to pass another element unsigned int array len. We no longer need to do that because it's already part of the vector. You'll be doing almost the exact same logic. Instead of getting the exact location as find element does, you will find the appropriate location and then overwrite that location with search. And so here I have an example run where I had test 1 has all those sizes, and those are the same tests that I have up above. So does anybody have any questions about the approach to the lab? Right, in that case, I will leave the Zoom open and I'll monitor the Slack, and I will also upload the video so you can refer back to it later.